So when you guys get that, I'm not exactly sure how they're doing it, but I was told that you guys, there's like a PDF form that you guys have to kind of check the boxes to pick your classes and all that kind of stuff. And it's in like a Canvas course or something like that. But what I was told yesterday is that they don't have chemistry HL listed on there as an option. They only have chemistry SL listed. So, and the person showed me the sheet, and it just has like chemistry SL1 and chemistry SL2. There's no option for HL at all. So what I told people to do was just to go ahead and check the box that has like chemistry SL2. So at least they know you're in the second year of the class. And then down on the bottom of the second page, I was told there is she showed it to me. There's a comment box, the bottom right corner of the second page. There's a comment box, and in the comment box, just write something like, you can say that like chemistry SL2 should be HL2, and then they'll want what's called the course code. And for HL2, the course code is SCB 243. Okay. The one that they have on there on the checkbox, it's SCB 241 because the SL ends in 1, the HL ends in 3. So go ahead and check the box for that one just so you have a science class selected. But then in the comments, make sure you include this. That way when your counselor looks at it, hopefully they'll look at it, they'll know that they need to use that code, because I'm not sure what happened and why the correct code's not on there for HL, since that's the class we have here for chemistry. But I just wanted to point that out before we get started today, because I know that you guys are working on filling those out this week and next week. Okay. All right. So now, having said that, our first part today, we're going to be talking about three more trends today. We're going to first talk about melting point, and we're only going to talk about it going across a period, because next time when we talk about group 1 and group 17, one of the properties we'll talk about for them is melting point as well, because it's going to be a little bit different. It kind of depends on like the type of bonding and the molar mass of substances and all that kind of stuff. So today, when we talk about melting point, we're only going to talk about going across periods and seeing how the trend changes. And then we will look at metallic character, and then we will look at what's called the acid-base character of oxide compounds that form with period 3 elements. So like period 3 starts with sodium, so it'd be like sodium oxide. And then the next one's magnesium, so then magnesium oxide. And then as I go across, then I get to aluminum, so there'd be like aluminum oxide. And then for the rest of them, they're going to be covalent. And so I would have like silicon dioxide. I might have phosphorus pentoxide, or there's a couple other ones for phosphorus because it can make multiples. So we'll get to that when we get down there, because that one's a little bit more complicated to discuss. But for right now, let's start with melting point. So there's a graph here. It's a bar graph. It's got the melting point of the first 18 elements. So hydrogen all the way through argon. Okay. Now, what do I see kind of happening on here? Anybody see anything kind of like repeating? What do we think? Yeah, so it's like it goes way up high and then it drops way down low. And then it kind of goes up again, but then it drops down low again. Okay. So that's kind of showing you those periods. Okay. Because elements 1 and 2, that's hydrogen and helium, they're kind of by themselves. We know they have some special unique properties and all that kind of stuff. So really, when I look at, let me erase that. When I look at here at element number 3, that's lithium. Number 4, that is beryllium. Number 5 is boron. Number 6 is carbon. So as I go from the metals and up to carbon, which is a nonmetal, it goes up. And then all of a sudden, all the other nonmetals drop down really low, like way lower than even the metals. But then when I get to number 11, I'm back to a metal because number 11 is sodium. So I'm now in the third period. And so sodium, and then 12 would be magnesium, 13 would be aluminum. So they're kind of going up again. And then it gets to the same group. It gets to number 14, which is, this is silicon versus this one is carbon. So the highest peak, they're both of those elements are in group 14, carbon and silicon. And then just like the other period, then it drops down. All these are a lot lower even than the metals on that period. And so the reason that it does this is it depends on the type of bonding that the elements do when they make compounds, okay? And so some of this we haven't gotten into yet because we don't get into a lot of detail about bonding until topic 4. So I'm going to do kind of like a quick version of it today, just so we can have the basic understanding of why this pattern's happening. But after we cover bonding in a lot more detail in topic 4, it will hopefully make a lot more sense, even more so later on. And so what it says kind of down here is it says melting point depends on the type of bonding. And so we have three, we have kind of some different types of bonds here. So we have covalent, ionic, or metallic, and it depends on the structure. And so for the structure, for ionic bonds, I can have a lattice structure where it's the negative and positive ions that are alternating in a grid. For covalent, though, there are two different types of structures. And that's why we see this trend. That's why up here, carbon and silicon are way high, even though, you know, they're pretty much, they're nonmetals, but all the other nonmetals are very low. And it's because carbon and silicon, they do this giant covalent bonding. The other nonmetals like nitrogen, oxygen, fluorine, and then phosphorus, sulfur, chlorine, the other nonmetals that come after carbon and silicon in their periods, they do molecular covalent bonding, okay? All the metals all do metallic bonding, okay? So as you go across, it says the melting point increases across a period as the strength of the metallic bond increases. So like, for example, as I go from lithium to beryllium to boron, it's going up. Same thing from like sodium to magnesium to aluminum. So as I go up or I'll go across the metals, it gets stronger. And so the melting point increases because the metallic bond's getting stronger. And then it says it reaches a peak at carbon and silicon. That's because both of those elements, they're not metals. Carbon's a nonmetal. Silicon is technically a metalloid. But both of them have these giant covalent structures. And I'll talk in just a second about kind of what that means just in general, because we get into that in a lot more detail in topic 4. But then after that, they decrease dramatically because the other nonmetals, they only do molecular covalent. So what's the difference between giant covalent and molecular covalent? Well, molecular covalent is like what we learned about last year. You know, like if I have water, it's just going to be like H2O, like this. It's going to be one molecule, okay? Or if I have carbon dioxide, it's going to look like this, and it's just one molecule. That's molecular covalent. They're sharing electrons, but they're individual molecules. So I have like multiple water molecules or multiple carbon dioxide molecules or whatever covalent compound. The giant covalent, and I'm going to switch over to my other notes rather than try to draw it for you guys and make your eyes bleed at my lack of ability to draw. Okay. So let's see. So these are actually in topic 4. So like I said, we get into a lot more detail, but today I'm just going to show you some pictures if I can get to them. Okay, so these are like molecular covalent. These ones that are about to come up here as soon as it stops scrolling and the screen catches up with me. So like methane is CH4, water, H2O, CO2, carbon dioxide. They all exist in like unique molecules, okay, with a certain number of atoms. So I'll wait for it to catch up. It's still scrolling. I've already gotten to the page. Jeez, I didn't know it was that behind. Okay, so these are molecular covalent, where it's its own unique molecule. So like this is one molecule of carbon dioxide. This is one molecule of water. This is one molecule of methane. So molecular covalents, usually they're liquids and gases because their bonds are pretty weak. So the ones that are after carbon and silicon, so nitrogen, oxygen, fluorine, and phosphorus, sulfur, chlorine, they're going to do these types of bonds, and their bonds are weaker. So that means they're usually going to have lower melting points. Okay. Things that are giant covalent, they look like this. This is why I wanted to show you this rather than me attempt to draw it, because it's not that easy to draw. But giant covalent structures, they're giant because they do not form discrete molecules. So just so that we have a basic understanding, things like carbon and silicon, they form these really giant structures like this, where they're still sharing electrons, so it's still considered covalent. But instead of having just one molecule and then another molecule and then another molecule, they end up kind of stacking around each other or on top of each other, and they form these big networks. So sometimes you'll hear them called networks instead of giant covalent, because they form big networks. And so because they're these giant networks, they have really, really, really strong bonds. Okay. Diamond is a giant covalent structure. The diamond is the hardest substance that we know of. Okay. Glass is a giant covalent structure. Glass is regular glass is silicon dioxide. So it's silicon. And so like here, the silicons are the blue, and every silicon is connected to 2 oxygen atoms, and then it's connected to other oxygen atoms that are connected to other silicons. Okay. And so for diamond is like this. It's just a bunch of carbon atoms, but they're all connected to 4 other carbon atoms. And they're kind of stacked. Kind of looks like cheerleaders making a pyramid. Okay. And so that's the main difference, is that things like carbon and silicon, they do this kind of bonding. And so their bonds are very, very strong. And it's it's not impossible to melt them, but it's like pretty close to impossible. So their melting points are so high because they do this type of bonding. Whereas the other elements, the other nonmetals that come after them in their periods, they just do that regular molecular covalent. And so that's why that's labeled like this up on this graph. So I'm going to clean it off a little bit. So if I kind of, labeled, so here's lithium, beryllium, boron, carbon. So I can see that the metals kind of go up until I get to carbon is the biggest one. So these all do metallic. Carbon does giant covalent. Then it drops down because this is nitrogen, oxygen, and fluorine. They all do molecular covalent. We do have neon here. It doesn't really bond to anything. Then it goes back up for the third period. So now I have sodium, magnesium, and aluminum. And again, it's not going up as much because these atoms are a little larger. But it is still going up until I get to silicon, which silicon, like carbon, because it's in that group 14, it does these giant covalent structures when it bonds. And then it drops down again. I have the phosphorus, sulfur, chlorine. They're going to do the molecular covalent. And then obviously argon is a noble gas. It's not really going to bond. So the explanation is kind of like I said, it's summarized down here. The melting point depends on the type of bonding and the structure. So the molecular covalent by far have the lower melting points. The metallic ones are typically a little bit higher, and the metallic increases as you go across the period through the metals. And then when you get to carbon and silicon, they do the giant covalent, so they have the highest on the whole period. Okay. And so you can see that for both the second and third period, we can see that it follows that same pattern of increasing all the way to the group 14, and then it drops down for the rest of the nonmetals on that period until you go to the next one. Okay, that's the general summary there. So you have some practice questions to answer. Now, metallic character. Metallic character is like how much like a metal is something. And in chemistry, like we can describe metals as being like, oh, they're shiny, they reflect light, they conduct electricity. Those are all properties of metals. But the actual definition of something having metallic character or being characterized as metallic in chemistry, it's just defined as how easily it can lose electrons, because metals want to lose electrons, non-metals want to gain electrons to become stable. So when we're talking about the actual chemistry definition of metallic character, it has to do with how easily an atom loses electrons. The more easily it loses electrons, the more metallic character it has. The less easily, the less metallic character it has. So it's going to be more non-metallic. Okay. So even though things like shiny and lustrous and conduct electricity and heat, those all are properties of metals, that's not how we define metallic character. So I wanted to clarify that, because a lot of things, if you ask somebody, well, what's a metal? They're like, oh, well, it's shiny, it reflects light, all kinds of things like that. It's malleable, you can bend it, like all those things. Yes, those are metallic properties, but metallic character is defined by how easily an atom loses electrons. Okay. Metals tend to lose their outer electrons to form positive ions. Non-metals tend to gain electrons to form negative ions, okay, just like we learned last year in chemistry. And as you move left to right, here's your trend across a period. So left to right across the period, metallic character decreases. That makes sense, right? Because the metals are on the left, and as we go across, we end up getting to the non-metals once we go past the stair-step line. So if I was talking about sodium compared to aluminum, sodium is going to have more metallic character because it's further left. Even though sodium and aluminum are both metals, sodium is more metallic than aluminum because it's further to the left. Okay. And so the reason that it decreases goes back to what we talked about last week, the nuclear charge stuff. So increasing nuclear charge and decreasing atomic radius means the outer electrons are held more tightly. And if they're held more tightly, guess what? That means it doesn't easily want to lose them. Okay. So since metallic character is defined as how easily an atom loses electrons, as I go across, my nuclear charge increases, my radius gets smaller, and so the outer electrons are held with a higher attraction. That means that it's going to be less metallic. Okay. As I go down a group, it increases down a group, and that's because we're adding energy levels. The atomic radius increases, we have more energy levels and more shielding. And that means those outer electrons, they're going to become easier to remove as it gets larger because they're further away from the nucleus. Okay. So once again, everything traces back to nuclear charge or the shielding and the electron energy levels. Okay. And so just make sure when you're asked about metallic character, you're thinking in terms of how easily an atom can lose electron, not things like being shiny or, malleable and that kind of stuff. Okay. All right, the last thing here is this acid-base character of the period 3 oxides, okay? Now, kind of like the melting point, this is going to make more sense when we do topic 4 with bonding, and also later on after we talk about acids and bases, which is topic 8. But the basic summary for what you need to understand right now is you need to understand that the first 2 elements, sodium and magnesium, those are metals. And so metal oxides, they're going to be basic in character. They're not going to be acidic. Over here on the right side, as I go across, phosphorus, sulfur, and chlorine, those are nonmetals. They're going to be acidic. The 2 in the middle are the 2 that you have to pay attention to. So silicon is technically a metalloid, but it acts acidic like the nonmetals. Aluminum is the tricky one because aluminum technically is a metal. But remember, I just got done telling you that it's less metallic than sodium because it's further to the right. Okay, it has lower metallic character or less metallic character. So because of that, that makes it actually behave what we call amphoteric. And down here it defines amphoteric. Amphoteric means it can act like both an acid and a base. So it's like it can go both ways. Okay, it just depends on what it wants to do. Really, it depends on what it's reacting with. And so the basic, what you need to understand is as I go across period 3 from sodium to chlorine, okay, I need to understand that the metal oxides are basic. That would be the sodium and magnesium. Okay, so metal oxides are those two. So they're going to be basic in nature. Aluminum oxide, it is an ionic oxide, but it has covalent character because that aluminum is not as metallic as sodium and magnesium. And so it's called amphoteric, which means that it could be act like a acid or a base. And then the remaining oxides, these are all non-metal oxides. They're going to have acidic properties. Okay. So what that means, because down here, one of the things it's going to ask you is to write equations for the reactions of these things with water. Okay. So what that means is if I have sodium, okay. Let me change colors. I don't like that I'm writing in yellow. So if I have sodium and it reacts with water, okay, it's going to make a base, okay, because I just got done telling you that sodium is basic, okay. So if I have sodium, it reacts with water, I'm going to produce the base that has sodium in it. So I'm going to make sodium hydroxide. Magnesium will do the same thing. It will produce a base. The sulfur and phosphorus and the one with nitrogen, they're going to produce acids, okay? And so if you have trouble on that, we can kind of discuss it on Friday. If you seem like you're having trouble, because I know these are a little hard to sometimes think of their equations, okay? But basically that's what that means. And then I would just need to balance this. So I need 2 hydrogens. So I put a 2 here. And then, oh no, wait, I lied. There's something missing. Na2O OH. I think it's in 2 separate spots. Sorry, that's kind of messy. That's another NaOH at the end there. But I want you guys to try to figure these out on your own. If you have problems, like I said, we can talk about it on Friday and kind of go over it in a little more detail about, what is the equation for these, but it has to do with whether they form an acid or a base, okay, when they react with water, okay. So we're stopping there for today. So because I wanted to